what happened. Okay, so we're going to go over those problems from the previous lecture that I asked you to work through. The first one asks about acid-base strength, and we're going to start by looking at bases. We have the base ammonia and hydroxylamine. So we could actually write reactions out for each one of these bases. If they're put in water, right, ammonia NH3 would interact in water to abstract a proton. A base is anything that accepts a proton. And by accepting a proton, we would create NH4 plus and OH minus. So the question becomes, how strong of a base is this? In other words, right, this is really an equilibrium because ammonia is a weak base. So how far to the right does this equilibrium lie? That dictates the strength of the base. The further to the right it lies, the more OH minus we're making, and the stronger the base is. And so we can determine the strength by looking at the Kb value. And the Kb value for this is 1.8 times 10 to the minus 5th. Now we're going to compare it with another base, hydroxylamine. And you're not familiar with hydroxylamine, but if you're given the formula, H3NO, and you know that it's a base, you should be able to write out the reaction with water, because any base in water is going to accept a proton, and we would get H4NO plus and OH minus. All right, now this base has a Kb value of 3.1 times 10 to the minus 8th. So, which base is stronger? Well, obviously, ammonia is the stronger base because the Kb value for ammonia is much larger than the Kb value for hydroxylamine. So ammonia, the equilibrium for the reaction with water and ammonia is going to lie further to the right, and you're going to produce a lot more hydroxide than you would with hydroxylamine. Now, the second part of this question asks, what's a stronger acid, NH4 plus or H4NO plus? Well, if you look at these reactions, you can see that ammonia here is acting as our base, hydroxylamine is acting as our base, and NH4 plus, that's the conjugate acid of ammonia. NH4NO plus is the conjugate acid of hydroxylamine. So we could determine which is the stronger acid, right? A conjugate acid, by definition, is something that acts as an acid. So in the reverse reaction, ammonium is acting as an acid, and NH4NO plus is acting as an acid. But we want to know which one's stronger. In order to compare the strengths, we need to look at the Ka values for those acids. And the one way we can look at Ka value is we could say, well, because ammonium, NH4 plus, because this is the conjugate pair of NH3, we know that the Ka value times the Kb value should equal the water constant for the dissociation constant for water. So Ka can be calculated by taking Kw, dividing it by Kb, and so 1.0 times 10 to the minus 14th divided by the Kb value, 1.8 times 10 to the minus 5th, that should give us our acid dissociation constant, which is 5.6 times 10 to the minus 10th. All right, so that's the Ka value for ammonium. Now we can do the same thing for hydroxylamine. For NH4NO plus, which is the conjugate acid of hydroxylamine. And we can say, well, the Ka then is going to equal the Kw divided by the Kb for hydroxylamine, 1.0 times 10 to the minus 14th, divided by 3.1 times 10 to the minus 8th. This is a smaller number, so you should already know that you're going to get a larger Ka value, because whenever you divide by a smaller number, you get a larger corresponding value. And so this gives us a Ka of 3.2 times 10 to the minus 7th. So the Ka value here is larger, which means that H3NOH plus is the stronger acid. So if we're comparing two things here, we could say, well, ammonia, NH3, is a stronger base, which means that it has a weaker conjugate acid. Hydroxylamine is the weaker base, which means its conjugate acid should be stronger. All right, let's go to the next problem. This was a problem about carbon dioxide dissolving in water. If we were to measure the pH of raindrop, and we saw that it was acidic, we would have acid rain. And this could be from carbonic acid dissolving into water to lower the pH. And so the question is, well, what's the concentration of H plus and OH minus if our pH values range from 5.2 to 5.6? Well, let's start with a pH of 5.2. What we can do is we can calculate the concentration of H plus by taking 10 to the negative pH, because we know that pH is equal to the negative log of the concentration of H plus. So it's a log base 10 unit. So 10 to the negative 5.2 is going to give us the concentration of H plus, and our concentration of H plus then is just going to be equal to 6.3 times 10 to the negative 6 molar. All right, now if we wanted to look at the concentration of OH minus, there are a couple ways you can do that, but one of the easiest ways is to use Kw, because we know that the concentration of H plus times the concentration of hydroxide should equal 1.0 times 10 to the minus 14th, right? The Kw value. So concentration of OH minus then is just equal to 1.0 times 10 to the minus 14th. Divide that by 6.3 times 10 to the minus 6th, and we get a value of 1.6 times 10 to the minus 9th molar. So at pH 5.2, we have 6.3 times 10 to the minus 6 molar, and hydroxide concentration 1.6 times 10 to the minus 9th molar. And that makes sense because at lower pH you should have more H+, which is why we consider it an acid. We can do the same exercise for a pH of 5.6. And we just say, okay, well, the concentration of H+ then is going to equal 10 to the negative 5.6. And this gives me a value of 2.5 times 10 to the minus 6th molar. The concentration of hydroxide then is equal to the Kw value, 1.0 times 10 to the minus 14th, divided by the concentration of H+, 2.5 times 10 to the minus 6th. And this gives me 4.0 times 10 to the minus 9th. So if you compare this to our last answer, we still have more H plus than OH minus, but the amount of H plus is lowered, right? We only have 2.5, so we've got about a little less than half the hydronium ion just by increasing the pH by 0.4 units. And then we've also increased the hydroxide in solution. We've almost doubled the amount of hydroxide in solution present. Okay, and so the next question we looked at before we left off was a strong base concentration calculation. And it said, well, if we have magnesium hydroxide in solution, and the solution, we measure the pH of the solution to be 10.05, what's the concentration of magnesium hydroxide there? Well, we know that the concentration of a strong base is equal to the number of hydroxides, the concentration of a strong base multiplied by the number of hydroxide present, which in this case is 2, equals the concentration of OH minus. So if we can find the concentration of OH minus, we can find the concentration of the base. Now we can find the concentration of OH minus by getting the pOH. We're given pH, but we know that pH plus POH equals pKw, which is 14. So 14 minus the pH, which is 10.05, should give me the POH value, 3.95, and that equals my POH. POH is just equal to the negative log of the concentration of OH minus. It's because it's a log-based 10 unit, we can say that concentration of OH minus then is equal to 10 to the negative POH. So our concentration of hydroxide is equal to 10 to the negative 3.95, and that's going to give us a value of 1.12 times 10 to the minus 4th molar. Now, in order to calculate the concentration of MgOH2, we got to divide that value by 2, because for every 1 magnesium hydroxide, you're going to lose 2 hydroxides, right? So this is just going to equal our concentration of OH minus divided by the number of hydroxides, which is 2. So if we take 1.12 times 10 to the minus 4th and divide it by 2, we're going to get a value of 5.61 times 10 to the minus 5th, and that's molarity. All right, so those are the answers to the questions from last lecture. Now we're going to move on into the next lecture, which is going to discuss how we deal with calculating the pH of weak acids.
So now we're going to get into talking about these equilibrium problems a little more. Because you have this partial ionization, you have this equilibrium that exists, we're going to have the acid that exists as well as the conjugate of that acid, the conjugate base, and H3O+. They're all going to exist simultaneously once this thing comes to equilibrium. So you have to use the icebox. For instance, if you have benzoic acid, okay, if we had a benzoic acid and we knew the Ka for benzoic acid, right, how would we figure out the pH? Well, we would have to set up that type of relationship where we looked at this from a equilibrium standpoint. All right. So try the annotation again here. We're just going to symbolize benzoic acid as HA. It's a little easier for me to draw that using this annotation tool. And we know that if benzoic acid is monoprotic, it's going to just partially dissociate. It's a weak acid. So right away that tells me I can't draw a single arrow. I have to draw a double arrow equilibrium. And I would get A minus and H plus. You could also think about this in terms of its reaction with water, right? Where we'd have H2O here and create hydronium ion, but the water wouldn't show up in the equilibrium expression because it's liquid. So we have to think about how this changes once it comes to equilibrium, because if I take benzoic acid and I have a 0.01 molar solution, well, some of it's going to dissociate, but not all of it, right? So I have 0.01 molar concentration, and initially I don't have any A minus or H plus. However, this will react to dissociate partially. So I'm going to lose a little bit of HA here, and I'm going to gain some A minus, and I'm also going to gain some H plus. So once this thing reaches equilibrium, my expression is 0.01 minus X. That's what my concentration equilibrium is. And here my concentration of equilibrium is just X and X. Now if we think about the Ka, which is the acid equilibrium constant or the acid dissociation constant, this is going to be products over reactants. So we would have A minus divided or multiplied by H plus divided by HA. All right. And if you look at benzoic acid's Ka value, it is 6.3 times 10 to the minus fifth. Well, we know that that's a small Ka, so is this thing going to favor the products or the reactants? This equilibrium is definitely going to favor reactants, right? And that's part of being a weak acid. It won't really dissociate that much. It'll just dissociate a little bit. And because it favors the reactants and Ka is small, the amount you lose here, X, is not very much. So we can say this is negligible and set it to 0. Now our formula becomes a little less complicated. And if we plug in our Ka value, which is 6.3 times 10 to the minus fifth, we can say, look, this is just going to be equal to X multiplied by X divided by 0.01, okay? So this simplifies to X squared over 0.01. So when you have a weak monoprotic acid, right, this is going to be pretty simple. We're just going to take the Ka value, 6.3 times 10 to the negative fifth, multiply it by the initial concentration of the acid. In this case, it's 0.01, and take the square root of it. And that will give us the value of X, okay? Now, X is equal to the concentration of the conjugate base A minus. It's also equal to the concentration of the hydronium ion, all right? So once we find X, I can calculate the pH really easily. All I have to do is take the negative log of, well, I can't spell log right today, apparently. Negative log of that value for X, right? Because that is equal to the concentration of H plus, and that's going to give me my pH, okay? So you can do this for any weak acid. For every weak acid we work with here, the Ka value is going to be so small that X is going to be negligible, which means you can always neglect it in your final formula here. There is only one acid where this is not true, all right? So if you have sulfuric acid, H2SO4, what can happen now is you get 2 protons, all right? And if you've been looking at your strong acids and your weak acids, you know that sulfuric acid there is listed as a strong acid, which means that this should be a single arrow dissociation to give us H plus or hydronium ion, and the conjugate base HSO4 minus, okay? Now, because sulfuric acid is a strong acid, that means that HSO4 minus is a very, very weak base. So it will not react with water to pick up a proton and go back the other way, right? And it's actually a better acid than it is a base. So in the second step, HSO4 minus can dissociate, but this is considered an equilibrium step, okay? So what does that mean in terms of what we're talking about here? Well, if I know the concentration of H2SO4, okay, that fully dissociates. Let's say I have 1.0 molar sulfuric acid solution, right? That's going to completely dissociate to make 1.0 molar hydronium ions and 1.0 molar of HSO4 minus, okay? Now, an interesting effect happens here. When that becomes negatively charged, all of a sudden, this proton feels a stronger attraction, right? So we can say, look, HSO4 minus, this is an acid, right? But this is also an anion, okay? And because you have a negative charge there now centered around your sulfur molecule, the proton feels a stronger attraction, so it doesn't want to dissociate as readily, right? And that's why we get this equilibrium. That's why this would be considered our first deprotonation step, right? And here, this will be our second deprotonation step, and that's a weak deprotonation. And I can't quite remember the Ka value off the top of my head right now, but it just so happens that this Ka value is not small enough to make X negligible. So whenever you have this type of reaction, right, you have to do a quadratic. Actually, it's probably easier for me to just tell you that instead of writing it out. So in all the weak acids we look at, you can make X negligible. That makes your life easier. You don't have to do a quadratic. But when you have sulfuric acid, you assume this first step is strong because it is. And then you take this concentration, carry it down here, do an ice table, but you can't make X negligible. You have to solve the quadratic. All right. So let me stop the screen share for a moment. What I want you to do is to try this with acetic acid. So work on some of these problems in the slide. If you have an acetic acid solution that's 0.1 molar, you should be able to determine the dissociation constant or the pH, right? Whatever I'm asking here for. So now I'm measuring the pH using a pH probe. I'm saying, okay, we have a 0.1 molar acetic acid solution. Let's calculate that dissociation constant. And you should also be able to tell me what the percent ionization is for some of these acids. Okay, so did you guys all see that on the screen share? I don't think you did. Hold on. So what I want you to do then is to work on this problem right here. All right, so spend some time this afternoon working through some of these problems. Here you're given the pH and you need to determine the Ka value, and then I want you to also do the percent ionization. Okay, remember the percent ionization is the concentration of H plus that you have at equilibrium divided by the initial concentration of the acid, okay, multiplied by 100. And what you'll see for all these weak acids is they're going to be 10% or less. For a strong acid, this is 100%, obviously, but for the weak acids, they'll be a lot smaller. All right. We talked about polyprotic acids a little bit, so I'm just going to kind of summarize some things with polyprotic acids quickly. Just like sulfuric acid, anytime you have a polyprotic acid, that first ionization step is always the strongest step, right? And it just gets weaker and weaker after that. And that's because the proton experiences a stronger attraction to the molecule because it becomes more and more anionic, right? Just like in sulfuric acid, you have a neutral substance, it's strong, it fully dissociates. In the second step, we have an anion now, the proton feels a stronger attraction, it won't leave the molecule as easily. So Ka2 would be lower for sulfuric acid than Ka1 is. So whenever you have a polyprotic acid, anything that's not sulfuric acids are a special case here. You can assume that Ka2 and Ka3 are so small, the extent of ionization isn't really large enough to affect the pH. Okay, which I say here, you can't do this for sulfuric acid. All right, so you could do this with carbonic acid. So I want you guys to also try this problem this afternoon. You have 0.0037 molar CO2, that's the solubility. And it goes through this reaction. All right, so if you assume that all that CO2 gets converted to carbonic acid, determine the pH of the water.